Hello. Welcome to the second webinar of the Heritage Science Academy, an activity of the IPERION Heritage Science EU Infrastructure Project and the European Research Infrastructure for Heritage Science. My name is Matthias Sterlich, and I will have the pleasure of moderating the webinar. The Heritage Science Academy represents the user group and training and dissemination activities organized in the frame of the project and of the infrastructure, and the majority of our activities are freely available to the entire community of heritage scientists and anyone interested in heritage science. Please do check our website and our announcements on various platforms. I have the pleasure of introducing the two speakers of today. Ina Reiche is CNRS Research Director of a joint team between the Research Institute of the High School of Chemistry and the C2RMF in Paris. She has been active in the field of heritage science for 20 years, exploring diverse topics, including the study of ivory and bones, which she will present today. She will be followed by Remi Petitcol, who is a European Policy Officer at the French Center for Research and Restoration of Museums in France, with a background in political science and EU law. He specializes in solutions for the integration of the heritage science community, focusing on establishing E-RIHS and on the development and management of the FIXLAB. Before I hand you over to our two speakers, just a reminder that please do post your questions in the Q&A section. And of course, you can use the chat to convey your ideas or even questions, which I will read out later, and our two speakers will respond to. Thank you very much, and I will hand you over to Ina.
Thank you very much for your kind invitation. Thank you for listening to our webinar, and I'm very happy today to talk about our research activities on Palaeolithic ivory using different FIXLAB accesses. So indeed, we are studying ivory artifacts from a very early period using different methods of particle physics. And of course, I'm not working alone. I work in close cooperation with different colleagues from the NewAGLAE facility in Paris, as well as the PUMA beamline at Soleil-sur-Coton, as well as many colleagues from archaeological university departments in Germany, France, in the United States, and even in Russia. So it is a really pan-European cooperation when we study this Palaeolithic ivory material. We are especially interested in ivory coming from the early Aurignacian. This is a period which belongs to the Upper Palaeolithic. It is dating back to 45 or 35,000 years now. And it corresponds to the first populations that arrived in Eurasia of the modern human. And with this arrival of the modern human in Europe, there was a sort of a cultural revolution connected, and which is also connected to the appearance of first art objects and personal ornaments, such as, for instance, the famous lion man made of mammoth ivory, or the Venus or other personal ornaments from the Hohlefels cave in southwestern Germany. And because these objects are so special, they're made of a very special material, mammoth ivory, there are many questions linked to these objects, which correspond to where the ivory is coming from, how the objects were produced, how were these objects used, and also, you know, a mammoth ivory is corresponding to the material extracted from the tusk of a very big animal. There's also symbolism in the materials choice made by these first humans, beside the fact that ivory has very special mechanical properties so that it can be easily carved and transformed into objects and tools. Beside the fact that we are dealing with art objects, ivory is also a biological material. It's a biomineral, and in its chemical and isotopic composition, it registers a lot of information on ancient ways of life. So we can find in isotopic ratios, in trace elements, even in ancient DNA, a lot of information on ancient ways of life. But we have to keep in mind that we are dealing with ancient objects that are generally coming from excavation, so they have been buried in the soil, so they are modified by alteration phenomena. We call them diagenic alterations, and so we have to consider alteration effects of these chemical and isotopic signatures in order to extract reliable information on past societies from these objects in the chemical analysis. So the aim of our study is to understand what kind of information can be gained from the chemical composition of these objects. We also want to know how this ivory material is modified over time. Is ivory material behaving differently from bone and antler? And what kind of chemical signatures can be used and then are kept in these materials even over very long time scales? And then when we find such markers, we will try to perform studies of where the material is coming from. We also try to do relative dating when absolute dating with carbon-14, for instance, is not possible. And then also we would like to establish a database on ancient ivories, because sometimes ivory objects are kept in museums without the archaeological context. In order to perform such research, we need to know exactly how ivory is made, or what kind of chemical composition has ivory. So ivory is a hierarchical biocomposite material. It is mainly composed of an organic phase corresponding to the protein collagen. And this is the sort of the matrix of the material. And we have fibers that are organized in a very special way and that are mineralized. And the mineral in these fibers is corresponding to hydroxyapatite. It is a non-stoichiometric calcium phosphate. And in this calcium phosphate, you can find many different trace elements as a function of the living conditions and also as a function of the burial conditions of the material. It's the same for isotopic ratios that are variable in the organic fraction mainly, and that depend on the living conditions and on the burial conditions. So this makes this material a very informative material from a chemical and isotopic point of view. And we would like to use this potential to gain more information about life in past societies. How we study this material. So one possibility is the facility in Paris, the NewAGLAE facility. It's a particle accelerator where you can use 3 amino protons to perform microproton-induced X-ray and gamma-ray emission. Here you have the setup with the different detectors, which is really optimized to have a very good detection limit for a large number of chemical elements. And so we can also perform different methods, and I will show you what kind of analysis we perform at NewAGLAE on ancient ivory as an example. Here I show you 2 types of spectra. On the left-hand side, you will find proton-induced gamma-ray emission spectra. So these are spectra that allows us to determine the fluorine and sodium content in ivory. On the right-hand side, you will find 2 proton-induced X-ray emission spectra. And here you see that you can determine qualitatively and quantitatively a lot of elements ranging from sodium to lead, or in some cases even to uranium, with good detection limits. So we have really a large range of chemical elements that are found in ivory that can be studied by these two methods at the particle accelerator NewAGLAE. Concerning ivory, we have some elements that are especially interesting, that are characteristic, that give us characteristic information. We have the main elements such as calcium, phosphorus, and magnesium that are the main and major and minor elements in ivory. So sometimes when you have an object, you don't know what the material is made of. This is a way to confirm that we are actually dealing with ivory. But we have to keep in mind that the magnesium content especially is often altered in Paleolithic or in ancient ivories in general. So there's a loss of magnesium. On the other hand, in ancient ivories, we also have very often an elemental uptake of different elements such as iron and manganese. So these are elements that are not corresponding to the ivory composition, but they are linked to the fact that there are alteration phenomena that have modified the ivory material. And then we also perform different kind of studies that I will show you to show that we have some trace elements that are actually well preserved, even in ancient ivory material, and that can be used, for instance, as characteristic marker of a region or no origin of the ivory. To check if we can identify ivory even on ancient objects on the basis of the magnesium content, we performed analysis of ivories of elephant and mammoth ivories of different ages. And as we can see, unfortunately, during alteration, we see a loss of the magnesium content. So in ancient ivory, you don't find this marker anymore, so you cannot use the magnesium content of ivory to identify it. So even, for instance, when you have an ancient ivory and you don't find magnesium, it doesn't mean that it is not ivory. So we have to be really careful when you use this marker. So it only works for very well preserved ivory. However, we want to extract information about ancient ivory. So we thought maybe other trace elements can be used as a site-specific marker in ivory. And so we studied different ivory material from artifacts from different archaeological sites throughout Europe, ranging from southern France to northern Germany and even Russia. Here you have some well-known objects from sites like Castanet in Dordogne or the Lion Man in Germany. And so when we study these trace elements in ivory, we are performing PIXI, but we are not only performing point analysis, we are doing generally mapping or element profiling, because we consider that a trace element, if it is well preserved or if it's biogenic, it should be homogeneous. The distribution should be homogeneous. And when we see, for instance, as in this case for manganese and iron, we see an enrichment of these elements and scattered pattern at the surface of the object by performing elemental profiling. So we think that this is a sign that these elements are not corresponding to the biogenic uptake, but to an exogenous uptake of the elements during the burial period. So these elements cannot be used as a site-specific marker or a characteristic marker of the ivory material used for the objects. We also checked other elements such as strontium, bromium, and zinc. And we took into account two facts. The first fact is that when we find trace element amounts in the same range or similar range as in modern or permafrost references, we consider that there's a good chance that these elements are actually biogenic and well preserved. And then we also change the profiles, and when the profiles are relatively flat, they are never perfectly flat, but when they are generally flat, we also think that this is a good sign to decide that these are potential site-specific markers for ivory, for tracing the ivory origin. And then we applied this method that we developed within the FIXLAB, IPERION HS, and Charisma project. We studied different sites throughout Europe. Here you see from Istowitz to Breitenbach, from southern Germany to from northern Germany to southern France. So different material, and indeed we could differentiate the different groups thanks to these specific markers, the strontium, zinc, and the bromium content. And we interpreted these markers as regional specific. So I think there is a possibility to trace the origin of ivory thanks to these trace elements. Of course, we also always have to check the preservation state of the ivory, but this can be done and at the same time using the PIXI analysis. And now I want to say something shortly about our current research. So we see regional differences, but we also would look more closer. We would like to look more closer, and we would like to know if we can differentiate ivories from different sites, because we have regions, for instance, in the Swabian Jura in southwestern Germany, where you have many different sites with ivory and different valleys, river valleys. And it would be perfect if we could also differentiate ivories from different sites, because in museums sometimes they are mixed up. So we study at the moment ivory material from two sites, from the Hohlefels cave and also from Hohensteinstein. And in order to have a more precise view on the chemical composition, we did some further methodological developments, also in the framework of the IPERION HS access. We combined, for instance, two PIXI and PV measurements, Rutherford backscattering at NewAGLAE, which allows us to study also light elements such as carbon and nitrogen that are characteristic of collagen. And this is, for instance, very important if we would like to know zones on the object that are well preserved with respect to the carbon content, and where we have good chances, for instance, to use these artifacts for the radiocarbon dating. Further, a chemical development was chemical imaging at NewAGLAE. We are not only doing point analysis or chemical profiling, we are also can do mapping now. And the NewAGLAE facility, or PIXI in general, is very well suited to study even lighter elements such as phosphorus that are difficult to detect using X-ray fluorescence, for instance. We can do mapping. And then also we would like to improve the detection limits for heavier elements, and that's why we also combined our investigations with analysis at the PUMA synchrotron beamline at Soleil. We performed XRF mapping, for instance, and we could do some very homologous analysis as at the NewAGLAE facility concerning, for instance, zinc mapping, and we even obtain better detection limits, so we can even trace lower amounts of zinc, strontium, and other heavy elements in ivory. And last but not least, we have also the possibility to combine this information, the XRF mapping, with X-ray absorption near edge structure spectroscopy, and this allows us to give further information about chemical speciation, and then we can better discriminate if a trace element is biogenic or exogenic. We have further hints on that. So this is work in progress. So with this combination, using different access providers or FIXLAB, we have at our disponibility really a total non-invasive chemical analysis of ivory, ranging from light elements to very heavy elements. And this we try, so within this FIXLAB research, so we could really establish a new approach concerning the study of precious ivory and ivory artifacts from the Upper Paleolithic period. We have many new data on these materials from different Paleolithic sites that are now discussed with our archaeological colleagues. We have more detailed insight into the alteration of this material and what trace elements are linked to diagenesis and what trace elements are site-specific or can be potential site-specific markers. We defined already some of these markers. We also have a possibility to determine the fluorine content, which is also a very interesting element for distinguishing subfossil and fresh ivory used on the archaeological sites. And now in our further research, we go on with the interpretation of this rich data that we have, but we always have to keep in mind that we interpret these data within by considering all other archaeological, environmental, and geochemical data. I thank you very much for your attention. I hope that you found this project interesting. I think I have to acknowledge before I hand over to Remi Petitcol, all my colleagues that have contributed to our research. Thank you very much.
Thank you, Ina. Thank you, Mattia, for the introduction. It was a very enriching way to see a project, or at least several projects of FIXLAB from Charisma to now IPERION HS. So now we'll be presenting you how FIXLAB can be a catalyst for heritage science and more. Sorry, the slides. Okay. So, and now I will briefly show you what is FIXLAB. Basically, FIXLAB is a distributed platform of stationary cutting-edge research facilities made available for access through IPERION HS. And this is a very important point, together with the related specialized expertise. It's not only cutting-edge facilities, but researchers behind the facilities that will help you develop your scientific project. This access is offered to heritage researchers to help address the major questions raised by the materiality of heritage science artifacts. So in terms of their genesis, manufacturing processes, alterations, conservation, preservation, etc., it can be a very wide range of research questions, but it has to concern heritage. This platform, FIXLAB, acts in synergy with two other platforms available within IPERION HS, ArcLab, which is access to archives and local repositories, and MoLab, which is a platform made of mobile instruments to study in situ the objects. And it also links to the joint research activities of the project in order to provide a more comprehensive service that leads to the co-creation of knowledge. So you can see on this slide a small word cloud of tags that people use in FIXLAB. So it can be composition, it can be linked to copper or the sorts of types of object. It can be linked to periods, historical periods. It can be related to a lot of questions, and all of them are addressed with this expertise. In terms of numbers, in IPERION HS, there are 23 research infrastructures available for access based in 12 countries. And in total, we offer more than 130 analytical techniques and always associated expertise. So a very brief history of FIXLAB. FIXLAB has been around for about 70 years. It's turned in about 18. It started in 2004 with only one provider, the NewAGLAE facility, which Ina mentioned earlier in Paris. And then we were lucky to have the involvement of Synchrotron Soleil near Paris and two facilities in Hungary, the Budapest Neutron Center and the Debrecen facility Atomkey, which specializes also in ion beam analysis. It was the case until 2020, the start of the current project IPERION HS, where we now have 23 providers among 12 countries and a much wider range of analytical techniques available. And the goal, the ultimate goal, is to make all these facilities participate to the European Research Infrastructure for Heritage Science, E-RIHS, which should start in the coming years. So our goal is to serve and support and help research in heritage science. So heritage, to distinguish what belongs to heritage science or what does not belong to the field of the project, we use this definition that was elaborated within E-RIHS and also IPERION HS and a much broader collaboration, which states that heritage science is the interdisciplinary domain of scientific study of heritage. It draws on diverse humanities, sciences, and engineering disciplines, and it focuses on enhancing the understanding, care, sustainable use of heritage so it can enrich people's lives, both today and in the future. It is an umbrella term encompassing all forms of scientific inquiry into human works and the combined works of nature and humans of value to people. So you see, it is quite a broad definition, but it really corresponds to the range of analytical techniques expertise we offer in the FIXLAB platform, and also what is offered in the other platform, which you will see in the future webinars. So in order to make our offer a bit clearer to the users, but also to the providers, we created 4 main categories of scientific platforms. The first platform is composed of large-scale scientific instruments, such as synchrotrons, IBA facilities, neutrons, but also proteomics, C14, etc. We also have specialized platforms for cultural heritage, for archaeology and paleontology, as well as paleoanthropology, and finally for restoration and preventive conservations. These categories do not mean that the facilities cannot do another thing, but it is a main domain of expertise. So in details, there is this breakdown of the techniques. So you see, it's more or less even between the categories. We have ion beam analysis, synchrotron techniques, neutron techniques, dating, and molecular analysis techniques for the large-scale instruments. But we also have very diverse techniques in the cultural heritage platform with radiography, tomography, X-ray techniques, liquid chromatography, scanning electron microscopy, etc. We also have very specialized and very interesting new techniques in the field of archaeology, paleontology, such as also dating, electron spin resonance, thermal ionization mass spectrometry, etc., ancient DNA analysis, which is a very useful platform. And also we have restoration and preventive conservation platforms, which focus more on environmental parameters measurements. It can be laser techniques for restoration, to do benchmarking, etc. So a lot of techniques. I don't have time to go into detail. I'm not able to. That's why, if you have very detailed questions, please contact the help desk. We have 2 addresses. You can write to either of them, but the first one is usually more for general inquiries. And if you have more specific questions, you can contact the FIXLAB help desk. And you can also, of course, contact directly the platform, the local contact points of the facilities. So a few examples I've selected following what Ina's presented earlier. So we have, for example, you can start with using ion beam analysis technique, either Atomkey or NewAGLAE. For example, to determine the elemental makeup of a material in a sample. Then you can use one of the 3 beamlines offered at the synchrotron Soleil to check, to go further into details, to verify or to conduct new experiments. And then, for example, Paige mentioned in her conclusions a bit before, you could go further with dating, radiocarbon dating, and also use some more specialized facilities, for example, the CNRS in Spain, which offers electron spin resonance, so paleomagnetism, and other techniques that you can see on the website. Who can access the FIXLAB platform? So very quickly, basically everyone working in a country in blue, and the UK. As you know, the UK has an agreement now with the European Union to participate through H 2020 projects, which includes IPERION HS. So for the purpose of IPERION HS, the UK is considered an associated country, and it will likely be the same for E-RIHS in the future. So in detail, the rule is that the user group leader, so the principal investigator, and the majority of the user group members must work in countries in blue, either light blue or dark blue, or a developing country. They can work, but they must not work in the country where the facility they require is located. So, for example, a Spanish researcher cannot ask for access to a facility based in Spain, or at least they can if they are the very minority of the user group, but it is not. The logic is transnational access. You have to cross a national border in order to access. It is also the case if it is remote access. You cannot have remote access to facilities located in the country where you work. But it is also open to people working in SMEs on the private sector, as long as they conduct heritage science research and they are willing to open their data once the data are generated. User groups must be able, obviously, to work on the objects they want to work with, so they need to provide insurance for the objects, etc. They must be allowed to do the work they want to do, and they must have the rights to disseminate the foreground data they have generated under the project. And if you are a non-European user or not in a country in blue, you can access the facilities, but it is very limited. It is limited to 20% of the users. So please check with the help desk or with us before submitting a proposal. We will give you more detailed information about that. So how to access? This is fairly simple. It is much simpler than in the previous projects. Now we have website, and everything you need to do is on the same email website. So if you have an idea for a proposal, either you are an expert user and you don't need help, or you can contact the help desk. We really recommend you contact the help desk because we have a lot of analytical techniques. Even if you already know it's free, and they will really help you refining a proposal and answer any questions you may have, either scientific or administrative. It doesn't matter. Then you have to log into the IPERION HS website, create an account if you don't have one. You select the tools you want in your access in the catalog of services, and then you add them to the cart. You agree with the access policy. You submit a proposal. It is fairly straightforward. You have a template to fill in. Then you wait for the peer review panel results, which take about 1 month and a half to have, depending on the feasibility and also the peer review panel work. Then you will be contacted by the access providers if the project is selected, and with them you will plan the access dates and the modality of access with the providers themselves. After the access, you have some duties. You have to send a user report and fill in a survey, and then in subsequent publications, you have to acknowledge the project and publish your data in open repositories. So you can see on this slide the cutoff dates for the calls, which are the same also for MoLab and ArcLab. The next one is end of June, this summer 2021. So you can check everything I've said on the website. And for more information, and including a video, step-by-step video on how to submit a proposal, you can check this email address, and the slides will be available on YouTube and elsewhere. So about the access modalities, more precisely, the access is always free of charge for eligible users. It's a big point, very, very important point. It includes travel and accommodation costs from your host institution or your home, basically, also to and back to the facilities, or facilities plural if you select several facilities. Users are liable to provide insurance for the objects under examination, and facilities are allowed to refuse access if you are not able to produce insurance for the object you want to study. And access are typically carried out within 6 months, but with COVID-19 limitations, it might be postponed to the year, basically, as long as we cannot travel as freely as possible as before. We also have a novelty in IPERION HS for FIXLAB. You can now request remote access to the facilities. Most FIXLAB facilities are able to provide such access modality, but it's better if you check with us by email before you plan the access. Providers are entitled to refuse that an access is performed remotely for whatever reason they may have, the safety of the object or insurance liabilities, etc. Samples can be shipped to the facilities. This cost is taken care of by IPERION HS, so you don't have to pay for it. You may have to organize it, but the facilities will pick up the tab. And we really want remote access to maintain a good level of interaction between the local researchers and the users, the external researchers. So we will require facilities providers to adopt online solutions, live streaming, Zoom webinars, etc., to have educational value and collaborative value of the access, even if you cannot travel. And finally, last but not least, this FIXLAB facility has been developed and designed with the final goal of being an important part of the European research infrastructure for heritage science, which is set to become an infrastructure in its own right in 2022 or 2023. FIXLAB will roughly be the same, but with some improvements, simpler eligibility rules. So national users will be able to access the countries located in the country where they work. Long-term projects will be accepted, so you will be able to have some sort of pass and have a project in several runs or several calls. Cross-platform projects, so to ArcLab and MoLab, will be possible, which is not the case so far. And we are also developing digital services and solutions within IPERION DigiLab, and it should be able within IPERION. However, there is one thing that is less appealing, but not all users will be awarded travel and accommodation grants. It will be a selective process, but still there will be a big budget dedicated to that. So the excellent proposals will be completely free, will be granted free access. So you have a very little chart of how IPERION is taking from IPERION HS, not only FIXLAB, but all the activities, is including taking the lessons of IPERION PP, which ended in 2020, and also from the DigiLab working group. I thank you for your attention, and I give very special thanks to Ina, who presented earlier, to Michel Menu, who has been a very decisive voice in structuring FIXLAB and also the heritage science community. He has retired about a week ago, and I was very happy to work with him. François Mirambe is now the FIXLAB work package leader, has kindly accepted to follow the steps of Michel in this part. Claire Pacheco, Quentin Lemasson, Florian Bourguignon, Yana, Mattia, David Beauty, Laura Benassi, and Zita have also helped me a lot in preparing this presentation and webinar. So thank you, everyone.
Thank you so much, Ina and Remi, for this super interesting presentation. And before we finish, I'd like to invite everyone to attend the next webinar, This will be the third webinar in our series, presented by Katrine Rose-Beers and David Bouty on MOLAP and MOLAP applications, specifically focusing on Islamic manuscripts. This will be on June the 1st at the same time.